I meant to say lecture 16. My apology if I say 18 later. I misread it. So this is lecture 16. Thank you. So this is lecture 18 on the general derivative. And so the general derivative, sometimes called the Fouché derivative, is how we would define the derivative for a function where we have, like, more than one variable in the domain and more than one variable in the range. If you go back and look at things, we've really only talked about how to differentiate things where we have either more than one thing in the range. That would be like a space curve, right? We had like t maps to x of t, y of t, z of t. We talked about how to differentiate those, right? Or we talked about partial derivatives of a function of, say, x and y, or a function of x, y, and z. So there we had 2 or 3 variables in the domain, but the range was still just one thing, right? So this is giving a definition for how we differentiate things where we have more than one variable both in the domain and the range. And essentially you can capture it by the limiting process as given here, and the insistence that there's some linear object that when you subtract it from the change in the function, that linear transformation, it reproduces all of the change in the function up to some linear term, which, so this limit, this Fouché quotient limit, expresses that idea. So basically a function is differentiable if it can be well approximated by a linearization, a linear function close to the point. In particular, the linearization is exactly the value of the function at the point plus the differential times the difference between where we're looking at and the point at which the linearization is centered. You can think of that as kind of like the generalization of the point of tangency for a tangent line. But essentially the differential is a linear transformation, and because of that we can look at it as matrix, its so-called standard matrix, which is called the Jacobian matrix, and you can either look at it as column vectors like so, or as row vectors like so. I would just point out that we've already, this isn't actually new. You've actually already been working with these in like special cases. So in the special case of paths, we just get like one vector as the derivative. That velocity vector is just a column, right? In the special case that you have functions with just one output, but they've got several input variables, then you have the gradient vector. That's what we've been doing more recently. So those are special cases. So again, like n equals 1, we get like r of t, and dr dt plays the role of the Jacobian matrix, whereas f of several variables, we have the gradient vector is playing the role of the Jacobian matrix. But in all cases, we can use the Jacobian matrix to formulate linearizations, like calculus 1, or the tangent line to a path, or we haven't done this yet. We'll do more of this soon. But actually this is going to be, if you looked at z equals to this stuff and it's a function of 2 variables, that would be the equation for the tangent plane as a graph. And you can also look at approximating coordinate change. Like there's a linear map which would approximate spherical coordinates or polar coordinate change at a point. Anyway, that's kind of esoteric a little bit. Let me just kind of go on from here. So like we'll see these matrices later, okay? That's why I'm mentioning them here. Anyway. So here's some explicit examples of linearizations. You can ask me about those if you have questions. If I have a homework problem on linearization, just remember, look in this section here. It's, let me see here, page. Let me just find you. Give me a second here. I got to look in the 2020 notes. In the 2020 notes, these examples are on like starting on page 181. So like right here is page 181. It's actually the top of page 181 in the current 2020 notes. All right. anyway, and then okay, great. So the question then is, what can we say about the linearization? Well, the linearization is related to the tangent plane, and so essentially, the graph of the linearization would be the tangent plane. And so we've actually already done that in Calculus 1, right? Like in Calculus 1, if you set y equal to f of a plus f prime of a times x minus a, that right there, this is the equation of the tangent line, right? This right here is technically the linearization of the function f at the point a, all right, of x. For what it's worth, I use that notation in Calc 1. It's the linearization of the function at the point. And so the graph of the linearization is the tangent line. Likewise, that parameterized tangent line we looked at to a path, well, that's also the linearization of the curve at the point. Okay, enough. Here's some pictures of tangent lines and the idea. The idea of the tangent line is it approximates the curve close to the point. The idea of the tangent plane, it approximates the surface close to the point, right? So the next section is a little bit technical, but basically the itch I'm scratching in this little subsection here is to try to connect the Fouché derivative with the ordinary derivative. And what this calculation here shows you, all right, this calculation, basically the point of it, I keep fighting with my mouse pad, the point of it is that if you work through it, the Fouché limit, the Fouché quotient limit, it reproduces the difference quotient limit that you've seen in Calc 1, and the relation between the differential and the derivative is that the differential is equal to the derivative times h. So like basically the ordinary derivative is the Jacobian matrix in this like one dimension goes to one dimension case. Anyway, if that's interesting to you, great. If it's not, don't worry about it. Here I calculate the best linear approximation for a function that goes from R2 to R3. I go through like gory limiting arguments. You can skip over them if you don't care. And I show that, in fact, it does satisfy the necessary limiting procedure characterization. It satisfies the necessary limit, and therefore we can identify it's the differential. And here's the formula for it. And then, okay, great, it's kind of an annoying calculation. The cool thing is we can just as well create that Jacobian matrix by just calculating partial derivatives with respect to x and y, because the domain has x and y as its variables, and there's three component functions, f1, f2, f3. And so, lo and behold, same Jacobian matrix. So which do you want to do? Partial derivatives or like explicit limits? I want to do partial derivatives. Okay, well, anyway. There are also some things which are true in general. In particular, differentiable implies continuous is still true. Remember, multivariate limits are tricky. Well, that discussion, it goes over to here too. So let's see here. If a function's continuous at a point, then all path limits exist, right? In the same way, if a function's differentiable at a point, then all directional derivatives exist. All right? So that's kind of the analog of that. And remember, the converse direction didn't work. If all path limits exist, it doesn't imply that the function's continuous at the point, right? The same thing happens here. You could have a function which has all directional derivatives existing, and yet it's not differentiable at the point. And that's what this example 16 does. This function, x squared y over x to the fourth plus y squared, for x, y not 0, and f of 0, 0 equals 0, we have previously shown that that is not a continuous function. And so since it's not continuous, it's certainly not differentiable. And yet this calculation here in example, I actually show that the directional derivatives, they actually all exist. They behave badly. For this calculation holds for b not equal to 0. But if you think about it, as b approaches 0, this guy gets, very, very, goes to plus or minus infinity as you approach 0. And yet, at 0, the calculation for b equal to 0, the calculation shows you that you get the directional derivative is 0. So there's a definite discontinuity in the directional derivative, directional differentiation. As you go across that b equals 0 line, you're like ripping from plus infinity to minus infinity as you go across there. And so that goes to show you that this example fails to have continuity of the directional derivatives. So in fact, that's the problem. If you can give continuity to the directional derivatives, then you can be confident that you can build up the general derivative from the directional derivatives. And so that's why we make this definition of continuous differentiability. Continuous differentiable means that all the partial derivatives exist and they're continuous in an open set. And then there's a theorem. If you have continuous differentiable, then it implies differentiable. And so that, that's comforting. The proof of this I give in advanced calculus. If you're interested, it takes me about a half hour. I can find the video for you if you're interested. It's not really part of Calculus 3 though, so I just mention it here. Next up, I give you an example of a function which is differentiable and yet doesn't have continuous differentiability. And so this is like a one-dimensional example, but here's the picture essentially. So like the red line is the graph of the function, and basically the thing is the graph is like super wiggly. Wiggle, 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 of the function, but the function wiggles really, really close to 0. It squeezes to 0. But when you plot the derivative in green, you can see that the derivative, while it exists everywhere, in fact, you can calculate the derivative at 0 and show that it's a half for the red function. So yeah, the derivative exists at 0, but it exists there discontinuously, right? There's not a continuity in the derivative. The derivative is oscillating madly at 0. And so that's troublesome, because that means that the tangent line doesn't really well approximate the graph in the following sense. Like if I said, oh, the tangent line has slope a half, so that must mean that the function's increasing near 0. That's not actually true. You could take successive points near 0 and see that as you go and increase values of the input, you decrease values of the output, because the function's actually oscillating. So you can find where it's decreasing. It's decreasing by very, very little, but it could still be decreasing on an appropriately chosen interval close to 0. So it's a pesky behavior. And you can build similar functions for more variables. I won't belabor the point here. And then finally, I give a definition for tangent space to a graph here. So just to summarize these couple pages of the discussion, basically I'm saying we are going to use partial derivatives of a mapping to define the tangent space. All right. And we're going to be looking at the context almost universally where the functions are nice, they're smooth, and so the partial derivatives exist, and because they exist we can build the tangent space from those equations using partial derivatives. The point of most of the discussion in this section is to show you that there are examples, relatively simple expressions, where you don't have the directional derivatives having continuity, and when that happens, some of the things we're saying break down. All right, so that's the point here. And of course, I also state the Fubini theorem, or actually Clairaut's theorem, that the partial derivatives commute. And I think you actually need to know that the second partial derivatives are both existing and continuous to get that. So you actually need continuity not of the first, but actually the second partial derivatives to get this nice result. And then finally, the end of this section actually has something computational to share, and that is that when we have a composite of two maps, there's actually a chain rule that says essentially you multiply the Jacobian matrices of the map to get the Jacobian matrix of the composite. And so what that means is we can actually derive chain rules for compositions of functions of several variables in terms of appropriate matrix multiplications. That is pretty neat. I have an example of that over here. So if we have, for example, the function going from R2 to R, and then the polar change map goes from R2 to R2, all right, then you can use the general chain rule. It says that the differential of the composite is the composite of the differentials, and that means that the matrix of the dg is the matrix of df times the matrix of dx. Okay, so the matrix of the function is just partial f, partial x, partial f, partial y. It's actually a row vector. It's 1 by 2, 1 row, 2 columns. Dx is a 2 by 2 matrix. This is the Jacobian matrix of the polar coordinate change map, which actually gives us cosine sine minus r sine r cosine. And then dg, well, g is a function of r and theta, so it would be a 2 by 2 again. So it's like this, partial g partial r partial g partial theta. So the general chain rule says that partial g partial r partial g partial theta is going to be equal to the multiplication of this row vector times that 2 by 2 matrix. And so when you actually multiply this out, right, when you actually multiply that out, you get cosine theta partial f partial x plus sine theta partial y yf minus r sine theta partial f partial x plus r cosine theta partial y partial f partial y rather. And so in the going back to partial derivative notation, this is the chain rule in this case. But it's, skipping ahead to our next lecture, actually what you can see here is that this is a different way to write that would be, I must find my pen. Where's my pen gone to? Here it is. So what we're actually looking at is partial x, partial r, partial f, partial x, plus partial y, partial r, partial f, partial y. And this guy over here is actually going to be partial x, partial theta, partial f, partial x. And then this is partial y, partial theta, partial f, partial y. And so these are the chain rules. There's a pattern here, right? And you can see it. It's actually a consequence of like matrix multiplication of the Jacobian matrices. Some students think that's interesting. Others don't care which kind of student you are. It doesn't actually probably matter too much, because what matters is that you learn how to take these partial derivatives, these chain rules, and I will show you many examples of that in the next lecture. So, oh, look, I even had it here, next page. So the pattern was actually that, and these are examples of these are examples of chain rule for functions of several variables. There are oodles and oodles of chain rules to learn, and we'll get to that next. So thanks, guys. And again, do not despair if you don't understand everything in this section. A lot of this particular section is devoted to giving pathological examples. So you're just looking for some big concepts here, and that's about it. Okay, thanks.